Welcome to Deep Tips. So, how are you, everyone? It's so good to see you all. So, in my previous video, we did circles, right? But today, I'm going to do permutations and combinations. So, children, the previous live streams on permutation and combinations were based on the basics of permutation and the questions based on permutation, and then in second live stream I did combination, right? So we did the basics of combination and the problems based on it. But in today's video we are going to do something trickier and very interesting. Yes, we are going to learn the circular arrangements in permutations. So this is something that comes in GRE exam or other competitive examinations. So it is very important topic and very interesting also. So we'll start in couple of minutes. I'm waiting for everyone to join. So grade 11 students and the students who are preparing for competitive exams, I'm waiting for you all to join my stream so that we can learn together. So when we talk about circular arrangements, we talk about a circular table or a conference room where people are sitting in a circle. So such kind of arrangements, right? And then we choose people. So I'll start that what is the difference in linear arrangement and in circular arrangement, because in my previous streams we have done questions based on only linear arrangements, but today we are going to do circular arrangements and maybe one question on linear also. Okay, just to recall and connect with that question. So I hope you all are joining soon, then we can start our today's stream. So I'm waiting for you all. So if you have joined, please write in the chat. Yeah, so okay, so let's begin. Just a minute. Okay, so you can see my screen now. We are going to start with our circular arrangements today. Okay. Yes. So when I say circular arrangements, what is special in it? But before we start that, let's take one linear arrangement and connect with the previous stream. So if I say I have places to fill in for 4 children, okay, I have 4 places to fill in for my 4 students A, B, C, D. So for if A comes first, he has 4 options to choose from, right? B has 3 places to choose from, and C comes third, so he has only 2 places to choose from. And the one who comes last, like D, suppose he reaches late and he has only 1 place. So for linear arrangement, when we choose the places or we make arrangements linearly, then it is 4 factorial or n factorial, right? But suppose now I have a round table. Okay, I have a round table with 4 chairs kept. Fine. Suppose A is sitting here, B came and joined A, then C joined in, and then D also came. So this is how they sat. Fine. Suppose I switched the places. Okay, A shifted here, so B moved here, and C here, and D here. So if I rearrange this scenario, it will look something like this: A here, B here, C here, and D here. So but if I look this arrangement from some other place or some other point, it is the same. In my first arrangement, B and D were sitting next to A. In my second arrangement, again B and D are sitting next to A. So there is no difference at all. If I again make another circle. Okay, it's oval. So it's more like a oval, and I again shift the place. Fine, I shift this A here, so B move here, and C here, and D here. Now this is my third arrangement. So if I keep on doing like this and I ask someone from the outside, okay, just tell me which one is different, so that my person might be surprised to answer this question, because all three arrangements looks the same, because it's a round table, and again A has B and D sitting adjacent to him in third arrangement also, like it was in first arrangement and second arrangement. So it's not making a difference. So the question arises, how do we solve questions when we have circular arrangements in permutation and combination? So the best way to do circular arrangements is fix one position. So if I have 4 people and I have to make the arrangement for them, so let's fix this A. Okay, now I have 3 places left. So now this B, C and D can arrange themselves, right? So I have fixed the place for A, so let's make one more arrangement. Now A stays here. Okay, now if I shift C here and B here, D here. Okay, now can you see? Now if I ask my friend, okay, is these two arrangements same, this first arrangement and second arrangement, then definitely you can point out the difference, because in first arrangement B and D are sitting adjacent to A, and in second arrangement C and D are sitting adjacent to A. So there is a difference. See, now we are able to change the seating plan in circular arrangements. So what is the formula here then? Fix one place, okay, fix one place and arrange the remaining. So that means if I subtract 1 from the total number of places, so it is n minus 1 factorial. So for circular arrangements, number of ways to arrange in circular arrangements is n minus 1 factorial. I hope you are clear with the concept and the difference between linear arrangement and the circular arrangement. Okay, so I'm back with a question, a very simpler one. So in this stream we will gradually move from easy to difficult, okay, so that you get a hold of the concept. So far we have learned the difference between linear arrangement and circular arrangement and how the formula is different for both of them. Okay, so now I'm taking a very basic, very simple example, and I will show you 3-4 variations in that example. Okay, so if I have 3 boys and 3 girls, okay, and I want them to sit on a circular table. Okay, so I'll make a circular table and I want them to sit here. So let's say I have places here 1, 2, 3, 4, 5 and 6. These are the 6 places I have kept for 3 boys and 3 girls. So my first scenario is there is no condition. Anybody can sit anywhere. Okay, so they can choose whatever place they want. So they can choose any place. I have not set any condition for them that okay, you should sit here or boys should sit here or girls there. They can sit anywhere. So now I have 6 places, 3 boys and 3 girls. So I told you in the introduction of circular arrangements that how we should do. We will fix one place. So let's say I fixed one place for a boy. So I can say okay, one place is fixed, so that one boy can choose his seat only in one way, but rest of the how many children, 5 children, because 3 boys plus 3 girls give me 6 children in total, and I have fixed the place for 1 child. So remaining 5 can choose their places in 5 factorial ways, like how we do, right? The one who comes first has 5 options to sit in, right? Suppose this seat is filled. Now the next boy who comes in or girl who comes in has 4 options to fill in. Okay, this is filled. Now third, then 3 options, then 2 options, and then the last seat which is left. That's why 5 factorial ways to fill in the remaining 5 seats. So that's why here we have 120 ways to choose any place, okay, or to make the arrangements for 3 boys and 3 girls when there are no conditions specified. Okay, this is my first scenario. Now let's move on to second case. So second case is, I'll change the color. Second case is when there is 1 boy and 1 girl sitting adjacent to each other, means they are alternate. So we can write here boy and girl at alternate places. 1 boy, 1 girl, like that. Or you can say boys are sitting adjacent to a girl, something like this. Okay, so let's erase these things. I'll be using this circle again. Okay, so now again I will mark how many places? 6 places. 1, 2, 3, 4, 5, 6. But now I want my boys, like how in class sometimes teacher makes the arrangement, okay, 1 boy and 1 girl should sit like this. So here 1 boy, okay, then he can't, next boy cannot sit here, so he can sit here, so I'm writing a B. Third boy can't sit here, so he can sit here only, correct? So then remaining places are for girls. So this is called boy girl arrangement. So here girl, and here 1 girl. So this is how we do boy girl arrangement. But how do we do if we have a huge number? So I'll just solve this. So first what you will do, okay, I have fixed 1 place for the boy. Suppose first boy, wherever he sits, that place is fixed for that boy. So he has only 1 place to choose, because when others are not there, only 1 boy has arrived, so he has only 1 place to choose from. Okay, now remaining boys, these 2 boys have only 2 options, 2 places to choose. Either boy 2 and boy 3 can sit like this, or they can switch the places. So into 2 factorial. Now remaining 3 girls, girl 1, girl 2, girl 3, they can sit this way, or girl 2, girl 1, girl 3, right? Or they can sit this way. They can switch the places in many different ways. So they have 3 factorial ways to choose the places. See, I fixed the place for first boy, so the boy or girl who came first has only 1 way to sit. He has to choose any place. Then rest of the places will be decided accordingly in case of alternate places, right? So when 1 chair is fixed, 1 person has already sat on the place, then like I fixed the boys, so remaining 2 boys have only 2 factorial ways to sit, because they cannot sit next to the boy. My condition says they have to sit at alternate places. Okay, so obviously they will leave these places, girls places, so I have put crosses here. So they have 2 factorial ways. Then the girls who come after boys, they can choose from these given 3 places, G1, G2, G3, and they can arrange their places in 3 factorial ways. So if we solve this, total ways for alternate placing is 2 into 3 into 2. that is 12 ways. So they can choose the places in 12 ways if they are made to sit alternate ways. Okay, so this is the second case in this scenario. Now let's take the third one. I'll draw another circle. Okay, I'm still going with 3 boys and 3 girls. Okay, so here is my circle. Still I have 3 boys and 3 girls, but now suppose boy and girl, third case, they will sit together as a couple. Okay, boy and girl will sit together as a couple. So when I have 3 boys and 3 girls, okay, they have to sit on the round table, but they are sitting together. Okay, here in this alternate thing, boy girl, they were not sharing the same like place here, like boy girl together. There were 6 places, but when I'm saying they're sitting as a couple, now we need to take it as a single entity. So here B1 plus G1 suppose is one couple, B2 plus G2 is second couple, and B3 plus G3 is third couple. So I have only 3 couples. So I kind of need only 3 places. So I can mark them like this, or maybe I can shift this down. So I need 3 places where I will put boy and girl together as one single entity. Okay, because it's mentioned in my condition that boy and girl will sit together. Their chairs are placed together. Okay, so now if couple 1 comes and they seated themselves here, C1. Now then that place is fixed, that they can't change the place once they have seated. Now for the remaining 2 couples, how many places are left? Like couple 2 can choose either this or this. So they are left with 2 factorial ways. They can choose only in 2 factorial ways. Then after this, if couple 3 comes, he will be left with only 1 place if couple 2 chooses this one. Okay, so this is how. But this is not the end of the question. Why? Because they have not given any order that if 2 chairs are placed here for boy and girl together, that where boy will sit and where girl will sit. Either boy and girl can sit here, or girl can sit here and boy here. They can always switch the places. So for every couple there are 2 factorial ways to arrange their chairs, to arrange their places. So they can arrange themselves in 2 factorial ways. Here 2 chairs are placed, so they can also arrange themselves in 2 factorial ways. Here also we have 2 chairs, they can also arrange themselves in 2 factorial ways, right? So that means 2 factorial raised power 3, correct? So these are the total number of ways in which we can make the 3 boys and 3 girls sit in the couples. Okay, so this is 1 into 2 into 2 into 2. So that is 16 ways. So couples can be seated in 16 different ways. Okay, now let's take 4th case. So this is the 4th case. See, in one question only we can understand 4 to 5 different scenarios. So let's go back. So in the first scenario, here is my question. I told you that 3 boys and 3 girls. So we fixed the 1 place and remaining 5 can sit in any way, 5 factorial ways, so 120 ways. In second case, we kept 6 places on a circular table and the condition was that boy and girl will be alternate to each other. So what we did, we fixed first place, whosoever comes first, and then 2 factorial ways for the remaining person. If boy comes first, then 2 factorial for the remaining 2 boys. If girl comes first, then remaining 2 for the 2 factorial for the remaining girls, and into 3 factorial. In my case I have taken boys, so 3 factorial for the girls. So this was the second case. Then third case that I explained just now was couple based case, where boys and girls were sitting together. So we considered them as a single entity, that they are sitting together. So suppose now in fourth case, I'm taking a different case now, where three boys will sit together. Okay, and three girls together. So they are not mixing with each other, they are sitting separately, like boys in a separate group and girls in a separate group. So like how we did for couples, we considered them as a single entity. Same way, now I want my boys, their chairs here, okay, and girls here. So they are clubbed together, and they are clubbed together. So boys and girls, they are going to sit like this. So maybe boy 1, boy 2, boy 3, or in any order, and here girl 1, girl 2, and girl 3. So suppose boys came first and they fixed this place. You must be wondering, ma'am is taking boys always first. So if girls come first, then they can always take whichever place they want to. So here boys takes the first place. So they have how many ways? If they sorry, if I fix the place for boys, there is only one way for them to sit. And then for girls, in circular arrangement, I have told you that one place we need to fix. So suppose I have fixed the place for the boys here. So boys come and sit here, then girls are left with only one option to sit, n minus 1 factorial. So if I have two seats here, okay, so two seats here, so one seat is fixed, then 2 minus 1 factorial, that is 1. Okay, now boys can arrange themselves in how many ways? 3 factorial ways. And girls also can arrange themselves in how many ways? 3 factorial ways. So we will multiply this thing with 3 factorial into 3 factorial. So these are the total number of ways. So we know 3 factorial is 6 and 3 factorial is 6 again. So 6 into 6 is 36. So same we did in the couple case that I explained previously. Here also, if I fix one place, that's why I have written 1, that for the first couple place is fixed, so he can choose only one place, right, that I have fixed. Then remaining two places, that is 3 minus 1 factorial. Okay, 2 factorial for the remaining two couples, and then every couple can arrange themselves in 2 factorial ways. That's why 2 factorial raised power 3. So here I have two places. One place I fixed for boys, so 1 for boys it is fixed. 1 girls can choose because only one place is left. Then boys can arrange themselves in 3 factorial ways, and girls can also arrange themselves in 3 factorial ways. That's why we have 36 ways to arrange in circular arrangement. Yes. So these are the 4 different cases. Now I have one more case to discuss with. Okay, that's little extended one. We have done about any place where no condition was there. Then second case we did alternate places, boys girls. Third case we did couple case, where boys and girls we clubbed their chairs and make it one couple. And fourth case we did 3 boys together and 3 girls together, they are separate. Okay, now in fifth case, suppose from these 6 children, 4 children they came in couples, 1 boy 1 girl. So I have 2 couples. Okay, or from 6 people I have 2 couples, but I have 2 individuals also. Okay, so 2 individuals who don't want to sit together. For some reasons they don't want to sit together. I have these 2 individuals. So how we are going to place them in a circular arrangement? Let's try to understand. Okay, so in this case, if I fix the place for first individual. So I have written here individual 1 or person 1, you can write P1 also. So then P2 doesn't want to sit here or here, correct? Because he doesn't want to sit adjacent to individual 1. So that means these two places are fixed for my couples, those who have come together. So I can put 2 chairs here for those 2 people, but I'll take them as a single entity. So my individual 2 will sit here, correct? So how do I do this question? I will fix a place for my individual 1, right? Then now these 3 places are left, but I know that this individual, second individual, is not going to sit adjacent to I1, correct? So he is left with 1 place only. So these two have only one option to sit on, and my couples, they can switch their places in how many ways? In 2 factorial ways. So I can write here 2 factorial. Also they can switch the chairs in both the cases, correct? So I can write here 2 factorial whole square. So if you solve this further, you get 2 into 2 into 2, that is equals to 8. So there are very limited ways to see 2 couples and 2 individuals who don't want to sit adjacent to each other. Okay, so this is how we do circular arrangements, where I have taken 5 different cases. Okay, so I have more questions for you. I'll be right back. So let's see who is connected with us. Hello Miss Sarita, welcome to the Deep Tips. Yeah, good evening. I hope you understood the concept. So we are starting our second question, which is also based on circular arrangements. It's a very interesting topic. So the question is, now listen carefully, it's different from what we did in the first question. Okay, I have few people, E, F, G, H, A and B. I have 6 people with me. Okay, and the question is, what are the number of ways in which these 6 people can be seated? Okay, they can be seated on a round table such that E and F are always together, or E and F must sit together. So this is the question, that we have to find the number of ways in which these people can be seated on a round table such that E and F, so I am highlighting E and F, they need to be seated on a like round table, but together. They must always sit together. So let's draw a circle. So if I fix the places for E and F, so let's take them as a single entity, because they are not going to shift anywhere. They can only shift in how many ways? 2 factorial ways, right? They will not go and sit between A and B. They can sit between A and B, but they will not be separated. E and F will always be together. We can have GH here or AB here, that doesn't matter to them, but they should be together. Okay, so for this kind of question, first of all, we have fixed EF. Okay, EF has 2 factorial ways to arrange themselves, and remaining G, A, B, H can arrange themselves in 4 factorial ways, correct? So this is how you can find the different arrangements in which these 6 people can be seated on a round table. So if you calculate this, we know that 4 factorial is 24, 2 into 24, so I have 48 ways to arrange them. Okay, So let's move on to third question. Okay, third question is a different one, a very interesting one. Okay, I hope everyone is clear with the concept that we are learning today. Now, the question says, find the number of ways to arrange 4 girls and 3 boys. Okay, so this question also I have split in 2 parts. So first part is, let's understand if I ask you to arrange in linear arrangement, and let's do circular also, so that we can connect with both of them. So if I am saying linear arrangement, that means I have total 7 places, because 4 plus 3 gives me 1 2 3 4 5 6 7. So for first child 7 places, for second 6, then 5 4 3 2 1, so 7 factorial. Correct? This is my linear arrangement. But if I have to take circular arrangement, I will fix 1 place, because I need something, right, to fix in circular arrangement. So remaining 1 2 3 4 5 6 children can arrange themselves in 6 factorial ways. So this is my number of ways for circular arrangement, which is definitely less than the linear arrangement. So the reason is, for circular arrangement there is no starting and end. That's why we need to fix 1 place, and that's why our factorial decreases by 1 value. But in case of linear arrangement, there is a distinct starting and ending, so that's why we take the n factorial. Okay, so now if I add a condition here, I add a condition that none of the boys are together. So which is same as the alternate that we did in our first question, but still it is not, it cannot be done the same way. The reason is, in my first question number of boys and girls were same, so making the alternate places was very clear and simple, because 1 boy 1 girl, there was no scenario where 2 girls were coming in between, right, because number of boys and girls were same. But here the twist is, I have 3 boys and 4 girls. Suppose if I try thinking using a diagrammatic approach, I can just say, okay, I am fixing a place for boy here, okay, then 1 girl here, 1 girl here, then 1 boy here and 1 boy here. Now here 2 girls, right? I might be thinking this way. Now my 4 boys and 3 girls are fine, but there may be case where girl is not here, 2 girls are here, correct? Or this girl, let's take it, okay, or here I have 1 girl but here 2 girls. So like this there can be different scenarios, because here number of boys and number of girls are not same. So how to do this kind of question? Any idea? Anybody can write in the chat if they have an idea that how to solve this kind of question, when number of boys and girls are not same in circular arrangement, and the question says that none of the boys are together. Anybody? Okay, so again we know that when we have such kind of circular arrangements, okay, I have 1 2 3 4 5 6 7 students, right? So we know that total possible ways in circular arrangement is 6 factorial, correct? That is equals to 720. Now if I take a case, let's draw another circle so that we understand better. Now I'm going to do it in a different approach. So if I take all 3 boys together, Now my question says that none of the boys are together, but if I consider, okay, my boy 1, 2, 3 are together, so my girls will obviously come together, right? If I get the answer for this question, I can subtract it from the total possible ways. Then I'll get the like unlike event where it comes that none of the boys are together. If I get the answer for, okay, what is the ways where all the boys are together, and I subtract it from the total possible ways of seating, then I get when number of ways when none of the boys are together. So let's understand how to calculate when all boys are together. Okay, so when boys are together, so now again let's fix one place for a boy. So 1 here, that boy has only one way, so B1 has only one way to sit. So what we will do here? Yeah, so now see here, what thing you need to care about, that you will not fix place for this one, we'll take it as a, yeah, we'll take it as a single entity, because there is no point of fixing one place. Anyways, I need to make them sit together because they all are together. You remember the scenario in the previous question where we did boys and girls separate, right? So here I have fixed the place for boys, so that is one way, correct? Okay, so then this is one. Now I have 4 girls who are sitting, they also have only now one place because they are sitting together. So these boys can arrange themselves in 3 factorial ways, because they have to sit only in this limited area, they all need to be together, correct? And here G1, G2, G3, 4, these 4 girls can arrange themselves in 4 factorial ways, correct? So that's why my answer is 6 into 24, which is 144, correct? So how did I do this? Here I took my boys as one entity and my girls as 4 different entities, or I can take them as together one entity also, because girls don't have any other option. When all boys are sitting together, girls are also sitting together. So there are 2 ways to do this. Either you say, okay, I have fixed one place for boys and one place for girls, and then boys are 3 factorial and girls are 4 factorial, or you can just do it in a different way also, where you say, okay, I am taking boys as one entity plus 4 girls, which is equals to 5. So now you fix place for 1 boys, then remaining 4 places girls can arrange in 4 factorial ways. Okay, so 1 into 4 factorial, and then boys can arrange themselves in 3 factorial ways. So this is one and the same thing. So this question can be solved in 2 ways. Either you consider in your mind, okay, boys and girls separate and boys are sitting together, girls are sitting together, and you solve this, or you take boys as one entity and girls, 4 girls separate, then 1 plus 4, 5, right? Where you then fix one place for boys and arrange girls in 4 factorial ways, that is n minus 1, 5 minus 1 is 4 factorial, and then arrange boys in 3 factorial ways. So that is 144. Now the question was none of the boys together. None of the boys together. So we know that there are total 720 possible ways for boys and girls to sit together. If I subtract the possibility when all boys are together, then obviously I get none of the boys are together. 576 ways are there in which boys can sit in such a way that none of them are together. Okay, I hope you are clear with this concept. I'll be back with another question. Okay, so thank you, Miss Rashmi Sinha, for subscribing on Deep Tips. Stay tuned for better learning. Thank you so much. Now we are moving to next question. This is question number 4. Okay, so in this question, I am posing this question for everyone. If you know the answer, please type in the chat. So this question says, if you have a team of 8 directors, 1 vice chairman, okay, and 1 chairman, so how many total people you have in the team? You have total 10 people. They are to be seated on a round table, okay, and they are to be seated on a round table. So that means this question is based on circular arrangements. Fine. So now the condition is chairman. Now condition I'm writing, chairman should sit between a director and vice chairman. I'm writing a VC. So this is the question. I have a team of 8 directors, vice chairman and chairman. They are supposed to be seated on a round table, and the condition is chairman should always sit between a director and a VC. So let's draw a round table. Okay, so now I will make 10 places here first, because 8 plus 1 VC plus 1 chairman, it gives me 10 people's team, right? So I am making 10 chairs here. 1 2 3 4 5 6 7 8 9 10. Okay, so children, let's fix the place for chairman. I am fixing it here. So this place is fixed for chairman. Okay, so if suppose chairman sits here, then vice chairman can either sit here or here, correct? So he has 2 places to choose from. If he has 2 places to choose from and he suppose chooses this place, then rest of the places can be kept for the directors. 8 directors, they can arrange themselves in 8 factorial ways. Like director 1 to 8, they can arrange themselves in 8 factorial ways. So this way I can find out the number of ways in which 8 directors, VC and chairman can sit on a round table, with chairman always sitting between VC and director. So what is 8 factorial? 8 factorial, we know 6 factorial is 720. So 720 into 56 gives me 40320, correct? And 2 into 40320 is equals to 80640. So these are the number of ways in which chairman, director and VC can sit on a round table, and this question came in GRE exam. So these kind of questions are mostly asked in competitive exams, and these are actually very easy to tackle with if you know the concept, and if you draw the diagram and just try to understand and focus what is being exactly asked in the question, so you can crack it very easily. Okay, so now let's do the last question of today's stream, question number 5. This is a very interesting question, and it's based on handshake, a very popular question in permutation combination. The question says, in a party people are doing handshakes. We do handshake in a party, right? So but not in corona, right? In this pandemic, the way of doing greetings has totally changed. So maybe you can say they're just doing elbow shaking, correct? So then also we can frame the question, you doing elbow shaking rather than doing handshaking. So this question is, in a party everyone has shaken hands, okay, with everyone else. So whosoever has come to party, everybody is doing handshake, and it was found that total handshakes or elbow shakes were 66. that 66 handshakes were exchanged, but there is a condition that no two persons have shaken hands twice. Means if I have done handshake with someone, I have not done it twice, only once. So these are unique handshakes. So tell me, what is the number of people in party? Okay, so and the condition is no two persons have shaken hands twice. Okay, so this is the major condition. No two persons have shaken the hands twice. So total handshakes in the party are 66. Everybody has done handshakes uniquely, no duplications. How many people are there in the party? Now you tell me whether it's a permutation question or a combination question. In this kind of question, first it is important to understand that whether it is permutation or combination. So when I am saying Dipti did handshake with Kirti or Kirti did handshake with Dipti, does it matter that which name I take first? It does not, right? Because I am doing handshake with Kirti or Kirti is doing handshake with me is one and the same thing. So here we have to use combination. So let's assume that there are n people in the party. So that means out of n people, if I am taking 2 at a time, total handshakes are 66. Okay, so NC2 equals to 66. So how do we solve combinations? N factorial upon n minus 2 factorial into 2 factorial is equals to 66. Correct? Now if I expand this n factorial, it is n into n minus 1 into n minus 2 factorial upon n minus 2 factorial, and I know 2 factorial is just 2, so cancel this. Now n into n minus 1 is 66 into 2 gives me 132. Now this is n square minus n equals to 132. So when I am bringing this here, I got a quadratic equation. So I am sure those who are in grade 11 or 10, they know how to solve this quadratic equation by splitting the middle term, right? Okay, so n square minus n minus 132 is equals to 0, and I know 12 times 11 gives me 132. So I can write here n square minus 12n plus 11n minus 132 is equals to 0. Correct? So n is common, n minus 12 plus 11 here, n minus 12 equals to 0. Now, so this is equals to n equals to 12 or minus 11. My handshakes cannot be in negative, there are no invisible people there. So n equals to 12. So that means in party there are 12 people who did handshake with each other without duplication. So this is how we solve this party question and how we do circular arrangements. So if you go through this entire stream from beginning to the end, I'm sure you will understand the circular arrangements very well. And the 3 streams of permutation and combination, stream 1, 2 and 3, covers the entire syllabus for CBSE and also a bit of competitive exams, because circular arrangements are not there in NCERT textbook. But yeah, I have covered it for the children who are preparing for other exams, and it's actually interesting to learn circular arrangements. So I'm done with the questions for today. So let's see who all are connected with us. Yeah, so yes, hi Ved. Yes, you are right. This is not for grade 10. This is for grade 11. So as I promised my grade 11 students that I will be doing this topic on Friday, so I fulfilled my promise. So, and I told you I will be doing trigonometry, so don't worry, from Monday onwards you will be having regular class on trigonometry, and we'll try to finish it in a week's time. okay, because trigonometry is a lengthy topic and I really need to like cover the entire sub parts of trigonometry, starting from the Pythagoras to heights and distances, because it's a vast topic, children. So I'll just split this topic in total number of streams, and I'll post that how many streams we are going to cover. Like in permutation combination, I wrote 3 because I was sure that we will be able to finish it in 3 streams. So same way I'll make a plan for trigonometry and make sure that both ICSE and CBSE students, we cover everything that comes in board exams. Okay, so don't worry about it, we'll definitely finish the syllabus before your board exams. And tomorrow I got requests from grade 7 students also that they are facing some problems in word problems of percentages. So looking at those requests, tomorrow 4:30 p.m. I'll be having a live stream on word problems of percentages. So if you have any siblings, friends, or family members who are in grade 7 or 8, you can tell them to connect with me tomorrow 4:30 p.m. in the evening, so that we can learn this topic in a much interesting way and not learning the formula, because percentage is actually something that is much more than the formula. Okay, so we are going to cover word problems tomorrow 4:30 p.m. If you have any query or any question, you can ask me in chat. Yeah, so yes, okay, so I have Ved connected with me. Oh, okay. So children, this is what I wanted to tell you. So we are done with circles of grade 10 entirely. If you watch my 2 videos on circles, theorems and questions, I'm sure whole chapter will be done. If you go through the questions that I have explained in my video, you go through those questions thoroughly and practice few more questions, similar questions, I'm sure you will be able to solve the board question. And this permutation combination is also done as promised. So now tomorrow I'll fulfill my promise with my grade 7 students and we'll do word problems. Okay, so stay tuned with me. Thank you so much. Please like, subscribe and share my channel so that more and more students can connect with me. Thank you so much.